Okay, so this is optics continued. This is double refraction. So what we are seeing here, we are seeing the wave meeting the surface at an angle, at an incident angle. It's transmitting inside of the material. And then it is exiting outside the material at the base. So there's 2 points of refraction, and there's also a little reflection ongoing at each of the surface. So there's 2 points of refraction and 2 points of reflection. But the reflection is only like 1% of the light. Okay? So like 95%, 99% of the light is refracted through the material at the two surfaces, at the top and the base of the surface, right? Good. So I drew this in the last note, right? So you will draw it again, and when you're drawing the reflection occurrence, you use like a dash line for the reflection, right? Good. Internal reflection. We have an incident ray at the critical angle to the normal, which is refracting at 90 degrees to the normal, which is parallel to the surface between the medium and air. This ray originated inside of the material. Then we have the incident ray at an angle larger than the critical angle, so it reflects at an equal angle to the incident angle. In this case, the incident angle is more than the critical angle, and that is why you will have total internal reflection. This can be represented by Snell's law equation, where N1 is the refractive index of the material, and then we have N2, which is the refractive index of the air. So we have sine theta I and sine theta 2. In this case, we put the critical angle as theta I, and we put 90 as theta 2 or theta R. If we rearrange the terms, we will get N2 over N1 is equal to be sine C divided by sine 90. In this case, N2 is equal to 1. So 1 over N is equal to be sine C over sine 90. One over N is equal to be sine C over sine 90. So N is equal to be sine 90 over sine C. Sine 90 is 1. So therefore, the final equation to represent total internal reflection is N is equal to be 1 over sine C. If we were to use the TIR equation, and we were to have a critical angle of 30 degrees, and we substitute it into the equation, we will get N is equal to be 1 over sine C, equal to be 1 over sine 30. Sine 30 is 0.5, 1 over 0.5 will give me 2.0. So N is equal to be 2.0. If we have a refractive index of N equal to be 1.6, and we want to find C, we will rearrange it to get N sine C is equal to 1. Sine C is therefore equal to 1 over N. Sine C is equal to be 1 over 1.60. So C is equal to be sine inverse of 1 over 1.60, which will give me sine inverse of 0.625. Therefore, C is equal to be 38.7 degrees. So you must put the sign for degrees, which is the circle to the top right of the number. Okay? All answers must be in 3 significant figures. All substitutions must be shown. Let us look at double refraction. With double refraction, we have refraction at 2 points on the body. So the wave enters the body and refracts and then exits, refracting a second time. So there's 2 incident angles and there's 2 refraction angles. The first incident angle is equal to be to the second refraction angle, and the first refraction angle is equal to the second incident angle. There's also reflection occurring at those 2 points, which will be seen in the subsequent diagram. If a wave enters and exits a material, it refracts twice. The second normal has a second incident angle. Theta I2 is equal to theta R1 because of Z angles. So that is a geometry law. Therefore, theta I1 is equal to be theta R2, and theta R2 is called the emergence angle. Theta I1 is called the I, or the incident angle. Double refraction is used in lenses. Concave lens diverges and convex lens converges. So that divergence and convergence is with respect to the principal axis. The average of the double refraction is on the optical axis OA. The focal length common F and the focal point capital F are on the principal axis PA. And we can see the equation 1 over F is equal to 1 over U plus 1 over V. The magnification of the lens is that M is equal to V over U, which is equal to be H prime over H. Here we have the convex lens with the optical axis running vertically through the middle. And we have the principal axis running horizontally through the middle. The ray is converging onto the principal axis, and that point is called the focal point. Okay? The distance from the optical axis to the focal point is called the focal length. Okay, so I'll give a detailed diagram of that next. Here we have the average of the double refraction is on the optical axis. So we would have refraction happening at the two surfaces, but for the diagram, the refraction is happening at the optical axis, which is the average, right, of the two surfaces. So the focal length F and the focal point F, common and capital F, are on the principal axis. This is the equation for the focal length. 1 over F is equal to 1 over U plus 1 over V. The unit is centimeters only you're using, right? And U is the object distance to the optical axis, and V is the image distance to the optical axis. The magnification of the lens is equal to be V over U, which is also equal to be H prime over H. So H is the height of the object, H prime is the height of the image, right?